Yeah, I do. Thanks. Quality model not quality.
I like it's only
Who tells you? Come. Public.
Public for all your friends and family.
I hope this is over. So, yeah. Whatever. How are you doing? How's the candidate? Okay, good. Pull this up and already had a big lunch, but the snacks look so intriguing that I'm going to steal some. You should grab it. Oh yeah, all the additives. It's yeah, it's good. Did you have time to take part in the phone call on Saturday? Because I had something around that time.
Hi. How are you?
Yes. I'm going to give up on Poornima. I'm just going to try to get the three of us. We need to figure out what the implementation is.
No.
And if you do that, we can have it all. If we cross the apple,
This one. Doesn't matter.
it's also part of the.
Yeah.
That's like saying I like you slightly more.
I guess, Paul's coming too.
Yeah.
Oh.
It's longer.
Yes, yeah, indeed.
The last time I was in exam, I had to go right for hospital.
No.
I promise I'll.
Can you please be less dramatic?
Okay, welcome to the D exam of Poornima. So it's the thesis defense, as you know. And has two parts. The first part is a sort of public seminar that you're going to be witnessing, and you're welcome to ask questions. But after this first part, you'll be asked to leave the room so that the committee can examine Poornima in more detail. So Poornima studied in IIT Madras, and a few years ago she came to Cornell, and she's been an asset to the department, I think, not just on the research side, but in terms of efforts for outreach, not only said to, I think she was instrumental in the formation of this women's group, not for the grad students to outreach, I guess, girls in the rural areas, right? The high school girls. But also she's being involved in some activities involving poor children in India, right? By Skype. Now, on the area of research, she joined us to help us to try to understand better these very interesting morphologies that local polymers can exhibit, which are known as bicontinuous phases. And those are as beautiful as they are elusive, but also very interesting from a viewpoint of applications. There are more and more people who are trying to make them for all kinds of very interesting advanced materials. And so trying to ask this question, can we make these morphologies? There are two aspects to it. There's the thermodynamics, there's the kinetics. And usually the first question one wants to understand is under what conditions these phases will be stable. And this has been basically the focus of this research that Poornima is going to show us. But that's the basis to ask the second question, which is kinetics. And she will show us some results on that as well.
Yeah.
Please.
Thank you, Fernando. Thank you all for coming. Feel free to ask questions at any time. I am very happy to present and talk about what I've been doing. So today I'm going to talk about how we can engineer ordered bicontinuous networks that are formed by blockopolymers with additives using molecular modeling. So these are three examples of three different bicontinuous phases. This is called a gyroid or a G phase. This is a double diamond or a D phase. And this is a Plumber's nightmare or a P phase. So blockopolymers are amphiphilic molecules where you have two polymers, unlike polymers that sort of repel each other, are attached end to end. So since they repel each other, they try to segregate, but because they're connected, they have to stay together and they form a variety of mesostructures. And because they form a variety of structures, each variety has its own set of applications. For example, this is just what polystyrene polyisoprene would be, and it's one of the most well-studied blockopolymers. So you can form lamellar phases, which is basically stripes of alternating monomers that are self-assembled, and these have very interesting applications in directed self-assembly and nanolithography. Or you could have ordered cylinders to form nanoporous materials or ordered micelles. And the focus of this talk is going to be ordered bicontinuous networks, and this is a gyroid phase. And these are very special because they have very good photonic properties. This picture here on the right shows the wing scale of butterflies. So the coloration that's green color is entirely due to the structure of the butterfly wings, and it has no pigments that are green in color. So just by tuning the structure, you can get a different color out of the butterfly wing scale. And over here, I show that somebody, this group has created the gyroid structure within their solar cell, and it seems to have better transport properties and better solar efficiency. But you have challenges because all of these are self-assembled structures. So each time you want to get a structure, you have to start with a new synthesis of a polymer. And lots of times you have experimentally, they see defects that have to be annealed for long durations. And sometimes even after annealing, there is a distortion or a defect in the structure, and there is some ambiguity in identifying the phase. And this problem of possessing more defects and more distortions is exacerbated near phase transitions. So the main goals of modeling this work is to understand the thermodynamics, which will tell you what exactly is a stable phase. And then we design strategies with which you can tune the morphologies that you actually want. And the third goal is going to be to partially explain some of the kinetic phenomena that we see. Because we are looking at the length scale of an entire polymer chain, I will be using coarse-grained simulations to study this self-assembly. I have two approaches to do simulations or modeling studies. One is called self-consistent field theory, where the polymer is modeled as a flexible Gaussian chain, and it's present in an effective field from its local environment. So you abstract out individual monomer information, and you have this polymer in this external field. and it ignores density fluctuations of local density fluctuations of the polymers. And it's useful in calculating free energies and unit cell sizes. It's basically an optimization algorithm, and it gives you thermodynamic properties at the end. On the other hand, I worked on using molecular dynamics with particle-based simulations. So we have these bead spring models. So the beads represent not one monomer, but a bunch of an oligomer or several monomers. And the local interactions are through individual beads. And because we're using a very soft potential, it allows a lot of overlaps, and it mimics an oligomer, and something like 20 beads would represent a long experimental polymer.
When you say density fluctuations, that is the density of the monomers itself or the environment? Both.
Both. This is a field description, so there are no monomers here. The polymer is modeled as a Gaussian chain, so it's a continuous curve, so you don't have monomers in the SEFT. And the big advantage of MD over MC is that, MD over SEFT is that you can get both non-equilibrium and equilibrium properties. It's a lot slower, so our approach is usually to use SEFT to get a broad picture of what the entire phase diagram looks like. And then in the regions of interest where we have bicontinuous phases, we sort of zoom in and use molecular dynamics to get a more detailed study of both equilibrium and non-equilibrium behavior. The next question is how we are going to engineer these bicontinuous morphologies. So the phase diagram of a pure blockopolymer is completely determined by two parameters. One is the volume fraction of one of the blocks, and the other one is the value of chi n, which represents the degree of immiscibility between these two blocks. So the chi depends on chemistry and inverse temperature, and n here is the degree of polymerization. So the phases here are, as you increase, you go from 0 chi n and you go to higher chi n, you have a disordered phase, and you get the lamellar phase, and as you vary the volume fraction, you can go from lamellar to gyroid to cylinder to micelles. But we are interested in this gyroid phase, which occurs in a very thin region. So once we get the gyroid phase, there is no way to tune the structure. We can basically get it only between 30% and 35%. You have the gyroid phase, and that's what you're stuck with. And so the way you work around this problem is to use an additive to expand the phase diagram. So from a 2-dimensional phase diagram, you go to a 3 or a 4 or a 5-dimensional phase diagram where you use an additive to start from a blockopolymer, let's say lamellar or cylinder, and then by using the additive, we can go and obtain the gyroid phase. Or in one case, I'll show that we start from the gyroid phase and we use an additive to get more complicated phase diagrams that you cannot get, more complicated phases that you can't get with just blockopolymer. The main parameter that distinguishes the additives is the size of the additive in relation to the blockopolymer. So there are 3 projects that I did. One is 2 phase selective solvents, and the solvent size is much smaller than that of a blockopolymer, about 1/100th or nearly 1,000th of that of the blockopolymer. Then we have a co-surfactant, which is smaller than a blockopolymer but not very large. And then you have an aselective homopolymer whose size is almost the same as that of the blockopolymer. And the choosing whether you have a solvent or a co-surfactant or a homopolymer comes with the 3 different strategies. So the solvent will basically swell both the A and the B structure, B phases unevenly. So if you have more solvent over here, you would swell A more, preferentially to B. A co-surfactant will sort of straddle the interface. It's a blockopolymer. Yeah, so here you have. So it straddles the interface, and it does not, it modifies the interface. It does not modify the bulk A or B domains. Then the third one is the homopolymer, which only swells the A domain. So it entirely goes entirely to here, and there is no preferential, it does not go into the B domains at all. So in all these projects, we start with a single architecture of this block copolymer, and then we add one of these additives, and we vary the volume fraction and see what kinds of morphologies we get. Okay, so the projects 1 and 2 were I already presented most of the results in my A exam. So I'm going to just briefly summarize the key results in this talk, and I'll focus a lot of the time to the third homopolymer topic. So what a solvent does two things to the phase diagram. First, it imparts mobility to the polymers, so you have an indirect temperature control. Once you add a solvent to the domains, the chains have more flexibility and you sort of lower the temperature. So you have it going from, if you start from this block copolymer, you go down and you go down in Cayenne. The other thing that it does is if you have a phase selective solvent, then it would preferentially partition into one of the morphologies. So in this example, if it's a B selective solvent, then the B domains expand, so the A domain shrinks, and so you're able to go in the horizontal. You can traverse the phase diagram horizontally. And so we studied a second solvent because you can independently adjust both the y direction, both the Cayenne and the volume fraction variables. So this was in collaboration with Professor Ober and his student, and they self-assembled PMMA block PHEMA with THF and methanol. So THF is PMMA selective and methanol is HEMA selective. And what they found in the experiments is that as you increase the methanol to THF ratio, you can go from the lamellar to the cylinder phase with an intermediate BCC or gyroid phase. And as you change or as you let it anneal from the BCC structure, they eventually got the gyroid structure. So the question that we would like to ask is gyroid the ultimate stable phase, or is there another phase, or will this change to either the cylinder or the lamellar phases? Since the solvent molecule is much smaller than the block copolymer itself, bridging these length scales is very difficult in MD. So we used only SCFT calculations for this study. And we have 4 different dimensions that we look at. One is Cayenne, one is alpha, which is the size of the solvent over block copolymer, and the volume fractions of these 2 solvents. So this is 3 dimensions of the phase diagram. And each plane belongs to one particular macro condition or one temperature. So if you look at this triangular phase diagram, at this extreme is the pure block copolymer, this extreme is pure THF, and this extreme is pure methanol. So you can see the pure block copolymer is lamellar, and we have started with the lamellar morphology, and as you increase solvent, as you add more solvent, it eventually becomes disordered. If you increase Cayenne, you still get a lamellar to a disordered transition in the THF rich region, but in the methanol rich region, you see the transition to disordered phase through a more complex or rich phase behavior. So from the lamellar, you get a gyroid, and then the cylinder, and then eventually it becomes disordered. So the conclusion is that the methanol contributes to a richer phase diagram due to its hydrogen bonding. The THF is a selective solvent, but it's not able to able to partition. Well, it is selective, but the degree to which methanol is selective is much larger. So the methanol side of the phase diagram is more rich. And now I'm showing you the phase diagram which matches closest to experiments. So the value of Cayenne and alpha is 30 and 0.01. And again, we start with the lamellar phase, and as you add more solvent, you get other phase behavior. So this is more THF compared to methanol, and this side is more methanol compared to THF, and this is intermediate. So these correspond to the numbers that they have formed. So in the experiments, as they go from BCC to gyroid, they see this transition from BCC to gyroid. So the gyroid is going to be the stable phase in the experiment. So the advantage of you doing all these phase diagram calculations is that we can also provide a design roadmap for the experiments to the experimentalists to go and do. So I have a 4-dimensional phase diagram. So you have 4 design parameters, and other studies in literature show that if you decrease the value of chi-n, the free energy barrier decreases. So if the free energy barrier decreases, it means that there is the kinetic effects are much smaller. And decreasing the degree of polymerization also concurrently increases alpha. And it's at this combination of parameters that we found the phase diagram that had BCC, gyroid, lamellar, and cylinders. One application for these copolymers that they synthesized was to form nanolithography. And starting from the block copolymer, the domain width can reduce to up to 75%. So if you have an application in mind and you pick the chemistry and the width, so these two are, once you fix the chemistry and width, you basically have the n is fixed and alpha is fixed, and then you can use the volume fractions to sort of go around, navigate the phase diagram and obtain the morphology that you want to obtain. Okay, so that's, yeah. The next thing that we did was study a co-surfactant where it straddles the interface. And one of the applications is you're able to tune the feature size of the gyroid morphology. So if we start with a long asymmetric block copolymer, because the B domain is much larger than the A domain, there is a tendency to form a highly curved microstructure that has high curvature. So if you have an asymmetric block copolymer, there's more tendency to form cylinders or micelles which have high curvature. And if you have a very short and a block copolymer with equal volumes, there is a tendency to form a flat interface or a lamellar structure. So the question is, if we combine these two, what can we form an intermediate curvature value and get an intermediate morphology? So there were lots of published experiments where they started with this cylinder and lamellar structure, and in the intermediate they were not able to identify the bicontinuous structure. It was the structure factor values that they got were not did not match with that predicted for the gyroid phase. And yet it was clear that it was not a cylinder or a lamellar phase. So because we have defects and maybe distortions, I'm using MD to study this behavior of blending a long block copolymer with a long asymmetric block copolymer with a short symmetric block copolymer. So is this actually going to be a gyroid phase, or do we get a defective or a distorted phase? So these are the results from the MD. As we vary box size, I'll also get different morphologies, and I will discuss that later. So we start with this extreme where you get a cylinder phase at most of the box sizes. And we also see a very interesting wood pile phase, which is a cylinder phase, but the two layers are pointing in perpendicular directions. This is a short-lived phase, but it's possible that so there are some kinetic effects that we see with the wood pile phase, and this would probably be a topic of future study. So as we increase the volume fraction of the short block copolymer, you get cylinder phases at various box sizes. And then in this interesting region, we see several phases. So the cylinder that you see here have now defects that are formed between them. So there are these tubes with these tiny connections between these tubes. And at smaller box size, we see a perfect gyroid structure. And if you increase the box size, you get a co-continuous structure, which is a series of these tubes and nodes, but then there is no order in the structure. If I increase the volume fraction, I see more of these co-continuous, disordered bicontinuous structures. And eventually you get defective lamellae and then lamellae structures. And this, again, reiterating the experiments that we get cylinder and lamellae, and in the intermediate we have these, we see some defective structures. The SEFT also agreed with the prediction that the gyroid is the intermediate structure. When we calculated free energy from the MD simulations, the free energies are within error bars of each other, and there is no clear stable phase. So it's likely that there are lots of defects because of this rugged free energy landscape. So the summary is that the field-based and particle-based simulations match the experiments at extreme values of volume fraction, and at intermediate volume, we have a rugged free energy landscape, and therefore the propensity to form defective or distorted structures is higher. And our free energy calculations showed that the defective phase was equally stable or within error as the gyroid and cylinder phases. And one of the future directions that this work could take was to study the stability of the woodpile phase relative to the cylinder phase. And then the key takeaway is that we also need better free energy estimation techniques with lower error bars to be able to do phase diagram analysis near phase boundaries. Okay, so now I will talk about the addition of homopolymer with the blocker polymer. And the key goal of doing this was to be able to access newer bicontinuous phases, and phases that are not just the gyroid but the diamond and the plumber's nightmare phases. So people have been trying to search for these newer bicontinuous phases for about 2 decades now. So the gyroid is the simplest one, where you have 3-fold connections. So this is a node which branches off into 3 different tubes, and then this tube will go meet another node which meets 3 other tubes, and so on. So this is the simplest node topology that you can get to form a network. The more complex ones are a diamond, which have 4 connectors within every node. A plumber's nightmare has 6 connectors within every node. So you have 1, 2, 3, 4, 5, and 6. And the IWP has 8 connectors within each node. And these are potential photonic bandgap materials. So both gyroid and diamond have, in other calculations, they were shown to have photonic bandgaps, and they exhibit iridescence also. So the diamond phase was only confirmed in blocker polymer systems as recently as June of this year. And there were experiments where the plumber's nightmare was thought to exist, but later examination of their X-ray profiles showed that it was a distorted gyroid and it was not a plumber's nightmare. So these new phases have not yet been confirmed in experiments. So I am doing modeling studies to look at regions where these phases are most likely to occur. Okay, and why are we using a large alpha for the homopolymer? And so there is a hypothesis going around saying that there is a pattern frustration present in these molecules. So we know that free energy eventually is going to dictate stability, but if we want to intelligently design additives or intelligently think of coming up with some additive, we would need sort of a hypothesis to go by and design an additive that would, be able to target this particular hypothesis. So this is a gyroid network, and over here you have this node and you have 3 different tubes. So the packing frustration hypothesis has got to do with the conformational entropy of the polymers that are occupying this network. So usually the radius of the node is higher than the radius of the tube because, it has to accommodate all of these 3 tubes coming together. So the node is typically bulkier than the surrounding tubes. So when you have just a regular blocker polymer straddling the interface, if it behaves entropically or conformationally the same as in the tube as in the node, then there is a vacancy in the center of the node, or there is a low density that forms at the center of the node. And so over here, then mixing entropy is sacrificed and the volume in the center is not utilized. The other scenario that can happen with the chain conformations is that to make up for the mixing entropy, only the chains at these nodes, they stretch. One of these blocks will stretch. But causing any kind of stretching these block copolymers is going to lead to a loss of conformation entropy. And if both A and B stretch equally, then you have this node, the morphology gets distorted and the node size shrinks. And it may be impossible to get a gyroid face. So the new proposition is that you want to preferentially fill the vacancy of the node with high conformation entropy additives. So a polymer is a high conformationally entropic additive. And so you want to, so the idea is to blend a block copolymer with a long homopolymer. And the homopolymer goes entirely within these A domains. The downside of this is that if you use a very high value of alpha, the homopolymer starts behaving like a dry brush. And since it's expelled from the interface entirely, there's also a higher tendency to form a macrophase separation. So it's possible that you try to blend these two together, but the homopolymer just completely comes out of the system. So there are all these different factors going into account that you have to have the right length. You need exactly the right window of the size of the homopolymer to get the structure. So these were self-consistent field theory calculations done in our group. It was published when I joined the group. And so you start with gyroid forming block copolymer and you add more homopolymer. So this is volume fraction of homopolymer added. And over here you have the size length of the homopolymer added. So you can see that they found a region of diamond phase to be stable and the region where the plumber's nightmare is stable. And the gray on to the right of this, you saw that there was evidence of some macrophase separation going on. But the downside of SCFT predictions is that it does not take kinetics into account and there's no density fluctuations. Especially near phase transitions, when you have pure block copolymer, it was shown that then the density fluctuations will shift phase boundaries and critical points to different values of parameters. So we used particle-based simulations to probe this phase diagram, especially near this around this triple point of coexistence of three phases. And going back, but to probe a triple point, you have coexistence between several phases, and the free energies will be very close to each other. So we need a very good free energy calculation algorithm or a free energy calculation technique to be able to differentiate between the stable phase. The challenges in studying bicontinuous phases is that due to computational tractability issues, we can only do one unit cell at a time. So our simulation box will only contain one unit cell because one unit cell takes about 100,000 beads to self-assemble into the structure. And then there is a sensitivity to box size in the three-dimensional morphologies. If you take a lamellar or a cylinder, which is a one-dimensional and a two-dimensional morphology, if you change the box size, the structure can rotate and sort of accommodate itself to the right unit cell size. So in this case, the lamellar is pointing towards you, and over here the lamellar is pointing in that direction. And so the directionality of the cylinder cell can also change itself according to if you increase the box cell size. And the third point is that we need free energy calculations because we do not know the box size a priori. So our free energy calculation technique should also be able to obtain what the actual unit cell size or box size is going to be. So in the co-surfactant example, the smaller box size had a gyroid phase, whereas a larger box size had co-continuous phase. So in this entire search space of box sizes, the gyroid formed at exactly one, or maybe sometimes if you're lucky, it will form at two different box sizes that are close together. And in all other box sizes, you will get these distorted or destroyed faces. Um, so I then started working on this method to calculate the free energy differences going from a disordered to an ordered structure. And the method I'm using is a variation of the thermodynamic integration. So the free energy change going from state 0 to state 1. So if you can parameterize this change in state using a variable, so this is a parameterized internal energy, and the free energy change is the integral of d lambda, the parameter, and the derivative of this potential with respect to lambda. And this has been used in a lot of alchemical transformations in peptides and proteins because you only have changed the identity of one of the molecules or one of the peptides. But in our system, we are not just changing the identity of a molecule from going from a homopolymer to a blocopolymer, but we are also undergoing a structural transition during this while going from 0 to 1. So we can't use this traditional uh, thermodynamic integration technique. So when you start from a disordered or at a reference state 0 and go to a target state, there is a first order transition. And usually you have hysteresis across this transition and you can't get an accurate free energy estimate. So what we do is construct another dimension and construct a continuous transition between the ordered and disordered state by using an external field that will force the system to go into order. And then I will remove this external field and increase current simultaneously, and then you can go from this point to another. And because this whole path is a reversible path, the free energy change is still the same, and you can go through this reversible path to get the free energy change. And the way this external field works is the simulation box is gridded into voxels. And if the target structure that I wanted to go as lamellar case in this example, if the bead of type A is in the wrong box, like the pink box, I give it a free energy penalty. No, not a free energy penalty, an energetic penalty. And if it's in the right box, I give it no penalty. So as I increase the value of C from 0 to 1, and as this goes from 0 to P, there is a continuous transition and this morphology slowly gets ordered. And to obtain the grid for U external, we smooth out transient fluctuations, and we take snapshots of 10 different structures. And from these 10 different structures, you sort of superimpose them to a common location and get a perfect structure. So over here, you can see all these fluctuations in these interfaces. And once you average them out, you get these very nice and clean structures. And we use this grid to impose the external field. This is an animation of what happens during this process when you start from a disordered to an ordered structure. So over here is the overall isosurface or the interface of AB domains. And over here you can see these molecular conformations. Brown is the homopolymer, and red and blue are the blocopolymer. On the right is the structure factor and the mean square end-to-end distances of the molecules. So right now the structure factor is flat because it's disordered, and as the system is driven into order, you will see peaks in the structure factor. And similarly, the mean square end-to-end distance right now is close to their optimum, is close to a homopolymer end-to-end distance. And the blocopolymer will stretch out because the two blocks repel each other. And the homopolymer will slightly contract because it is confined within these tubes and nodes of the blocopolymer. So, yeah. And this is the first branch. And by the time you reach the end of the first branch, you already form a completely ordered structure. And as you remove the external field, the structure is maintained, and so now you have this. And I can also go back and forth reversibly between these two states. And so now you can calculate the free energy difference. So by running longer simulations, we are able to get smaller error bars. And then as a function of box size, the morphology shows a clear minimum in the free energy. So that means that the optimum box size for this gyroid face at this structure is between 23 and 24. So these are phase diagrams comparing the SCFT, and the dots over here show the results from the MD simulations. So at high alpha, we get the diamond phase to be the most stable phase in particle-based simulations, and at the value of 0.722, we get diamond and Columbus nightmare in this point to have free energies that are very, very close to each other. And over here you have diamond and gyroid with free energies very close to each other. So we can't do coexistence simulations because these unit cells have completely different box sizes. So we can only infer coexistence from the equalness of the free energy. And the interesting result is that at lower value of alpha, the diamond phase is actually more stable. So in this 9 points that we studied, the diamond phase was at least stable or coexisting with another phase. The cylinder phase is not stable in our simulations. The diamond gyroid has a higher degree of coexistence, has a higher region of coexistence than an SCFT. So it seems that ignoring these fluctuations in SCFT at lower alpha is not, so that the fluctuations become more important at lower alpha, and it seems that the diamond is stable at a much larger region than actually predicted by the theory. Another usefulness of this technique of reversible path thermodynamic integration is that you can calculate the free energy of defects because you have this external field. So you can impose a defect in the system. You can decide what defect you want to impose, and you can impose a defect, and then you can compare the free energy between the defective and the perfect structure. So this is a perfect structure because this node has 3 branches of the gyroid, and this is an imperfect structure because in this network, this node has 3 branches, but then they're also they loop back and connect with each other. And sure enough, the free energy of the perfect structure or ideal structure was lower than that of the defective structure. And the happy box size of the defective structure is, because it's distorted, it requires a larger box size to have the lowest free energy than the ideal structure. Okay, so this is the macroscopic picture of free energies. And now I'm going to talk about the packing frustration hypothesis and what the polymer conformations are. So we're looking at the microscopic structure. So to probe the packing frustration hypothesis, I am trying to correlate between the chain location within this network and its end-to-end distance. And by chain location, I mean the location of the chain's center of mass. So each, for example, you would divide the simulation box into the same box cells that we apply the external field in. And based on local density, you can assign the voxel 1 or 0. And then an interface would be defined as the edge of the cluster of these A domain regions. And over here, you can actually see not a defect, but it's a fluctuation of this lamellar interface. So it's, and this is periodic. So you get this zeros over here, you get 0, 1, 0, 1. And then you calculate the distance of within each cluster. Di is calculated as the distance from the interface. So Di here would be 1 means it's at the edge of the interface, and a higher value of Di means it's farther away from the interface.
What's the
Distance from the interface. Sorry. And the node is defined as the set of voxels that are farthest from the interface. So in this case, because it's a lamellar face, it's sort of an extended node. So you have a lot of values with lot of numbers with value 3. But then you can define a center of mass for this cluster again and calculate the center of the node, the geometric center of mass. And so this, and then I randomly pick either this or that. In this example, this is going to be the center of the node. And then from here, I will calculate DC, which is the distance from the center of the node. So if this is the center of the node, this is a distance 1, then 2, 3, 4, 5, 6. So each point within the network has a value of DI and a value of DC. And each point within the network has some chains that are sort of near that point in the network. And those chains have an end-to-end distance. So we plot a correlation between the number of chains at that particular value of DI/DC and the end-to-end distance. So the number of chains is given by the height of these 4D color maps, and the end-to-end distance is given by the color. So green, or greenish blue, means it's a happy conformation, or it's at the ideal conformation that a polymer should have. And red would mean it's more stretched, and blue would mean it's constricted and it feels constriction. So the color maps for all the 3 different types of morphologies, the G, the D, and the P, what we saw is that the end-to-end distance is approximately 1, or it's pretty happy. And the only places where it's either stretched or constricted are where the number of chains are also very small. So in that sense, statistically, these have a much less contribution, and you have most of the chains have a good, have a happy conformation, and there is no pattern frustration in these morphologies. But so the other thing that you can obtain from this particular map is the geometry of the network. So we can calculate what the radius of the node is without visual inspection. So we have an algorithm to do it now. So the maximum value of DI, or the point which is farthest away from the interface, is equal to the radius of the node. And when you go away from the center of the node, you can mark the boundary at which the node ends, because now you know the radius of the node. And everything beyond this gray curtain is a tube. So you can also calculate the distance of the tube, or the length of the interconnecting tubes. So you have a node, and then you have the tube, and then you have another node. So you can calculate both the radius of the node and the length of the interconnecting tube. And you can also calculate the thickness of the tube, which is the maximum value of DI within the tube. So when you go from a gyroid to a diamond to a plumber's nightmare face, I haven't shown, these are the results over here, that the radius of the node increases. So gyroid has the smallest node, then the diamond has slightly bigger one, and the plumber's nightmare has the biggest node. And the tube width is constant outside the node. So the tubes are almost like perfect cylinders outside the nodes that connect, outside the nodes. And then the interconnecting tubes, or the L tube, becomes smaller. So the tubes become shorter, and the R tube is smaller. So they are both thinner and shorter. And when you look at the gyroid structure, because it's stable in a wide region of volume fractions, what we observe is that when it's at the edge of stability, so when it's coexisting with gyroid, with diamond, the value of R node and the value of R tube are almost the same. So there is no pattern frustration, but then also the geometry has been sacrificed. So you can't go to a higher volume fraction, because then you can't distinguish between the nodes and the tubes. Whereas if you look at the stable value of G, which has no competing faces, the radius of the node is larger than the radius of the tube. It means that you have a very well-defined node at the cost of having a constricted conformations for the homopolymers. So there is some pattern frustration, but the geometry sort of alleviates the pattern frustration and allows the structure to be stable. Compared to despite having no pattern frustration, this is at the borderline of stability. So that concludes the pattern frustration, the microscopic story. And finally, we are moving, once we have the free energy phase diagram, we can also look at the kinetics of the self-assembly. So in molecular dynamics, we quench the system from a disordered structure. So we take a disordered structure at 0 chi-n, and then we quench it to the target chi-n. And then the domains sort of grow, and then they align and form the structure. And this would be the rugged free energy landscape where you have, and so you start from this disordered structure which has a high free energy. And then you have this rugged free energy landscape, and this would be the most stable phase. But it's only this region that's dominated by energetics. The bottom rugged free energy landscape is sort of dominated by kinetics. So it's possible that depending on the starting conditions of the simulation, you can go into a metastable phase, or you can go to an entirely different phase than what's stable, or sometimes you can fall into the stable phase well, or sometimes you just go to a distorted or a defective well over here. So they're all, but so the true equilibrium is still what is given by free energy, but then it's possible that you're stuck in one of these wells and you have to run a very, very long simulation to actually be able to go from this well to the eventually stable well.
I mean, is it subjective at all, though, to how defective does alpha have to be before it becomes a separate phase, beta?
These are topological defects. I don't think there's a good framework to describe these topological defects. Or what I mean, I don't even know if there's a framework that says, given the structure, these are all the possible defects. You can guess 1 or 2 defects from what you see, but you still don't know that you've covered all the possible defects.
So does that mean the answer to my question is no, it's not subjective, or yes, it is subjective? It sounded like yes, it is subjective.
It's subjective, yeah.
Okay.
It is subjective, yes.
And what's OOT?
Sorry, order transitions.
Oh, I thought it was out of time.
OH is order transition. Yeah. Yeah, because sometimes you can go from an ordered phase to another ordered phase. That's what I was getting at. So I ran some simulations for one particular volume of box size at one particular combination of homopolymer and blocopolymer. And based on the random seed, you can get, I found either a diamond phase or a cylinder phase. And I've only done 2 trajectories so far. So I don't have an ensemble of trajectories, and so I don't know the entire landscape. And then we also define what a degree of supersaturation is. So the higher degree of supersaturation, the higher the propensity of, the higher these free energy barriers are supposedly. And so when you have higher chi-n values, you have a higher degree of supersaturation. And when you decrease the chi-n values, you have a lower degree of supersaturation. And this is the 2 simulations, one for the diamond phase and one for the cylinder phase. And if you look at the structure factor peaks, as an evolution of time, I'll play the movie in a second, but what we see is that the second peak in red is goes through a very sharp spike when this domain splits into 2 different networks. So that's like the signature of formation of the diamond phase, is that when you have something that splits into 2 networks, you get the second one goes to a peak and then sort of settles slightly below the first peak. The cylinder phase is completely different. You just have the first peak keeps on growing and settles at a value, and all the other peaks are much smaller. So the one on top is the diamond phase. And you can see the coarsening of domains from when you start. And then it has already split over here, and now you have 2 different networks. And this would be the cylinder phase, where you have coarsening of domains, and then they sort of already align to this first peak. And then when all these defects go away, then this sort of settles down into this value over here. And if you decrease the degree of supersaturation, within a single simulation, we see both the cylinder and the gyroid phase. Cylinder and the diamond phase. So we have a disordered structure, and then the cylinder starts to form. So the second peak has died, but suddenly you can see the second peak has risen, and you have the diamond phase. So you have coarsening of the domains, and then you have cylinders pointing in this direction. You'll see it right now. So these are the cylinders that again become separated into two domains, and you have this peak that increases and goes. So from these movies, at least the structure factor seems like a good candidate that can distinguish between the cylinder and the diamond faces. So there are lots of methods to study kinetic phenomena like string method or forward flux sampling that require a good order parameter, and structure factor may be one of the things to explore. Yeah, there are other experts in kinetic phenomena in our group, so it could be a topic for them. So in conclusion, the reversible path thermodynamic integration was developed and used to calculate free energies near phase boundaries, and it had very good resolution that was actually comparable to SCFT. So you can actually go and study phase transition regions, and it can also be used to calculate free energies of very specific defects. So the gyroid phase, across these three topics, the gyroid phase now can be obtained at a much larger volume fraction. So this is a pure block copolymer which can only form the gyroid phase at 33% of A plus or minus 3-4%. But using a surfactant, you can go to much smaller domain sizes or much smaller sizes of volume percent of A. And using a block copolymer, you can go, using a homopolymer, you can go to a much higher volume fraction of A and still obtain the gyroid phase. So there, I only looked at chain selectivity, and the size of the additive, but there are other things that you can tune, such as chain architecture. You can study functionalized nanoparticles, or you can change chain stiffness and have a rod coil block copolymer. And I'm working with a master student to now study rigid molecule with a flexible side chain. So it not only can form lamellar and gyroid and cylinders, but it can also form liquid crystalline phases. And the final takeaway is that despite a very good knowledge of the thermodynamic phase diagram, there is still poor kinetic understanding for block copolymer self-assembly. And order transitions that I looked at with commensurate box sizes, it seems that the structure factor is a good order parameter to look at. And would like to thank my my committee members for lots of years of guidance. Professor David Morse in Minnesota gave us the SCFT code, and Francisco and Juan Carlos basically helped me kickstart my PhD and taught me a lot about running simulations and all that. Escobedo Group has been a great support throughout the years. Jonathan, Brian, Steve, and Professor Zia Jonathan has been a really good sounding board, so thanks. In NSF and Exceed for their resources. And this is actually a woodpile face, and this looks like a smiley. So. Thank you for listening. I'll be happy to answer questions.
Question from the audience?
Earlier you said you were looking at using some polymers because they have a high entropic configuration to put in the middle of the nodes or steroids. What kind of polymers are you looking at? Well, were you looking?
This is just a model. So this is a very generic model that we have used.
How long, roughly? Like, were they of all sizes? Or?
So I varied alphas. My blocker polymer is 18 beads long, and these homopolymers are between 12 and 15 long. So that's what I studied. Thanks. Yeah.
I'm sorry if I don't understand this well. When you were talking about the radius of node and radius of the tube, I don't understand the correlation. Like, Do you want them to be same or?
No, nobody knows what it is supposed to be. So this was sort of the first study that explained what it actually looks at the microscopic picture and tells you what the values are. Sorry, what was your question again?
So like in different phases, like your gyroid phase,
Correct.
or cylindrical or tangent. So like, what is the correlation? What is the takeaway?
So you expected that for a node that has more connections, it will be a positive node. Right?
Correct.
And you saw that.
So that was correct. Yes.
Not correct, but
Yeah, that's the expectation, and that's what we found. But then there was no prediction for what the tubes are going to be. So you have more number of tubes. Those are two things. There could have been two scenarios where the tubes just become thinner or the tubes become shorter. But what we see is that both things happen together. And the reason we're doing this at the triple point is because these have very similar total volume fractions of the A domain. So you're sort of keeping the volume of the A domains constant, but you're changing the morphology. So then you have the same quantity of A, but then it has to go in a different percentage as into the nodes and then different percentage into the tubes. So that's the difference. Yeah.
The first two project topics had interesting correlation with experimental data that exists around.
Yeah.
How would you ratify the third project with experimental results? Is it possible?
So no, so it's only this year that there was one paper published that found a diamond face, and they used PSPI and PI. Yes, I think. Sorry, P. So till this year, nobody had confirmed this face. I mean, the theory has been predicting this for a while, but we don't have, or we are very slowly gaining experimental confirmation for it. So this is it's a very futuristic project.
And along those lines, the size of the box that you consider for all your situations, does that experimental evidence provide you any idea as to what the size of the box should be for it to be realistic?
Yeah, so what the experiments get are structure factor peaks, which is the first peak is the inverse of the box size. So we do have, and from our simulations also, we know the box size. But they have a completely different value of alpha. They have a much lower value of alpha than what we explored. But it is possible to compare experiments and simulation. The experiments can get a very specific unit cell size, and we also have a box size as our unit cell size. And the theory can also predict the unit cell size. So they all match. They have the same trends. Yeah.
So the homomorphism that you add, is it the minor phase or the major phase?
Minor phase.
And I'm just wondering, like, what makes it occupy the node region?
It occupies both the nodes and the tubes, but it occupies the nodes more than the tubes.
Why?
To alleviate pattern frustration, and also it's a dry brush, so there is more space in the node for it to occupy. So it's happy to be in the nodes.
Okay, so then two more questions. Please give the room so that we can continue. Yeah.